broken links for a lot of the readings previously, but those should all be fixed now. So there should be links that will take you either to Canvas or to the actual reading. I just fixed these this morning, so if you tried to access them before that, they probably didn't work. These are R for data science, which is sort of some of the stuff we're doing today. But the other thing I wanted to mention is these ones, which are the green. This is the Singer and Willett book. So I mentioned that so this is the book. I am not requiring any of the reading from this one, but it is recommended. That book is really good. So so I'd suggest, you know, trying to access those chapters if you can. But what I've linked to instead is this from UCLA. You've probably seen this. They do a lot of different stuff where they show things in different software and whatever. So they walk you through the code to run the stuff from that chapter. But we can also just up here get rid of all of that and just go to ALDA, Applied Longitudinal Data Analysis. And so this is the table of contents to all of these. And the reason I'm showing this is because they have this statistics books for loan, which I don't really know what you do, but that is one of the books that they have. So I don't know if you need to request access to it or what. You might be able to request access to it through the university library also. I'm not sure, but that's what I've linked to there because those are more like suggested readings. I would have made them required, except I didn't want to require you to buy the book. So it's kind of up to you. Okay. So before we hop into the lecture today, is there anything anybody wants to check in on in terms of, did you have any troubles with R or anything? Okay. So let's go ahead and just jump into the slides then. So today is the only lecture that we have on deck that is, we're for sure, my cat already. We are for sure going to get into some modeling stuff later, but we're gonna start out with some basic, well, not basic, but we're gonna start out with some data structuring stuff in R. Okay, so this is, I think, the only lecture we'll have that will really focus on R code outside of like modeling stuff. Okay, and when we talk about, like, next week, we're talking about plotting. So we'll be talking about making predictions from your model, and then how you take those predictions and actually plot them to kind of understand your model at a deeper level. So I'll, you know, mention things in passing there about how the code works or whatever, but this is the only one that's really devoted to it. Okay. So the agenda for today, we're going to talk about restructuring data. Then we're going to talk about fitting models. So the restructuring data is like the whole first part. Then we'll have our little 5-minute break, and then we'll talk about fitting models. We're going to talk about an unconditional model, random intercepts model, and random slopes model. Okay, so all models you hopefully should be familiar with from the first class. Okay, from there, we will then jump into homework 1. And as I mentioned in the announcement, my goal is to always give you at least the last 30 minutes of class every time I assign a homework. Okay, it is meant to be a homework, so it's not really a lab. They're sort of similar, but not exactly the same, because you have the other script that I'd like you to turn in each week too, right, which is your 1 point. So so that's how we'll do that. If we end up with more time here, if we end up with like 45 minutes, great, but I'll try to make sure you have at least 30 minutes. Okay, so if we get to like 11:30 and I'm not through everything that I was hoping to get through, I'll just kind of stop at that point and we'll finish whatever we were going to do the next class. All right. Okay, so learning objectives: understand the basics of moving data from a wider format to a longer format, and understand the basics of LME4 Elmer. Okay, LME4 is going to be the primary package that we use for modeling in this class. We will use others though when we talk about the variance covariance stuff in week 4. I actually already have a draft of those slides up. We'll be using NLME, which is really the predecessor to LME4, but it allows you to specify different residual variance covariance matrices that LME4 does not. And then week 6, I think it is, we get into Bayesian stuff. So then from there, we will be talking about the BRMS package, which stands for Bayesian Regression Modeling with STAN. Okay. Okay, so today will be highly applied, and I hope mostly review. If so, the only real difference is it'll be in R. So if you have a lot of familiarity with R, a lot of this will be review. Okay. If you have like very little experience with R, then some of this might feel a little fast, right? So this is like always the balance I'm trying to weave here. But please do feel free, like even if you're bored, that's fine. Just please stick with us. But if you're feeling lost, please do interrupt me and ask questions, all right? Because this is the reason I'm devoting a lecture to this is a difficult topic, right? And it's also a super important one because when you're sort of munging data with R for my multi-level modeling, this is something you have to do super, super regularly. You really regularly have data that's wide and you need to move it to a longer format. My kitty cat is distracting within the first 10 minutes of class, so that's great. Okay, quick schedule announcement too. I sort of mentioned this also in the announcement, but I was looking at the schedule and how I had things sort of lined up, and I think I made a mistake of basically assigning homeworks on days when we already had really sort of intense topics. So that would be limiting the amount of time that we had to spend on those topics. So I decided to push back homework 2 and 3 by a week. So homework 1 is still assigned today and it's technically due in 2 weeks. But again, like you can turn it in whenever, just make sure you don't get too far behind because that would be a bummer at the end of the term. Okay. But homeworks 2 and 3 are now pushed back each a week. So homework 2 is going to be assigned week 5. Homework 3 is going to be assigned week 7. And then they're going to be due it on weeks 7 and 9. Okay. All right. On to restructuring data. So please do follow along. I'll give you a minute here. Please go ahead and launch R. And then you should have this current data. It's either going to be available to you through Canvas, or if you cloned the repo, you will see it in the data folder. Okay, so as you're doing that, I'll kind of talk through this code a little bit. So library tidyverse, right, is going to load a bunch of packages. It's going to load dplyr, tibble, ggplot, per, all sorts of packages. And you'll get a message printing out telling you which packages it's loading. Okay. Then I'm going to read CSV to get this current data, which is a CSV. Notice I'm using read_CSV instead of read.csv because that's from the readr package. And it's just a little bit nicer than read.csv. It's a tiny bit faster. It's not tons faster, but it's a little bit faster. But better, I think, is just that it comes in as a tibble, which basically has nicer printing properties, right? There's a few other things too, but that's the main part. This here code. So here, this is called namespacing, right? So here is the actual package name, and then here is the function within the package here. All right. So this is another way to access a function within a package without actually loading the package like I did up here with library tidyverse. Okay. And then what this is doing here goes to your project directory. So we have a folder structure. We should have an R project. Okay. And let me show you what I mean by that real quick. Wrong folder, going to the wrong class. Okay, so let me switch my share real quick. And so here's an example, right? This is my folder structure. but here I have mlm2.rproj. Okay, this is the project for the entire course. And what is nice about using here is when I say here, it will figure out that there's an R project there and it will build a path to that project. So it matters not at all what any of these folders are that precede that folder. It will figure out that that is the root directory. Then I can be working on a file that's say in scripts right here. So I'm actually nested in another folder deep. But when I say here, it's going to say, okay, this is where I'm at. So my specific script I'm working in might be in this scripts folder. But when I say here, it'll put me here. And then I can go into the data folder from there and grab the current data. Okay, so that's what that is doing. And as I mentioned before, I would really encourage you and really like you to use the here package. It takes a little bit of getting used to, but it really helps for reproducibility. Okay, after you've done that, you should have the current data loaded. So give me a thumbs up emoji if you have gotten to that point. Okay, I'm going to give you just another minute because I see a few are still working. And then if yep.
Sorry, can I ask a quick question? At this point, like I'm familiar with here, but usually I have like the data in my own folder. So using GitHub, do I need to like open the desktop app and have that be my sort of like working directory that I'm working from?
So if you have cloned the repo, then this code should work exactly, right? All that you need to do is probably launch that mlm2.rproj.
Okay, then yeah, I don't think I've cloned the repo at this point, so maybe that's what I need to do.
Okay. If not, maybe start a new R project and then just put the data in that.
Yeah, okay. Is there a way to, just for today, that I can just download that CSV into my own like folder?
Yeah, so it's on Canvas.
Okay, thank you.
The current data is, so that's probably going to be the easiest way.
Yeah, okay, thank you.
Any other questions? Okay, I'll give you just one more minute. Okay, hopefully you've been able to get that far. And so now you can follow along with me. All right. So if not, keep working on it while I give you a little bit of background about the data. Okay. So this is data that is from a multi-level modeling book, and it's just something I found online. There's 405 children who are in the first 2 years of elementary school. So it's a repeated measures design. Okay. So we have 4 repeated measures for every student. And we're looking at antisocial behavior and children's reading recognition skills. Okay. So the format of the data currently looks like this, right? So we have an ID for a student, and then we have their antisocial skills score for the first time point, the second time point, the third time point, and the fourth time point. Then we have their reading recognition skills for the first time point, second time point, third time point, fourth time point. Okay, and then something over there too. I don't know what it is. I can't see. All right, so let me actually just get this going in RStudio myself too, in case I need to share that. Let me make sure. Yeah. Okay, so that is, we've got kid gen, which I don't know what that is, mom age, and kid age. Okay, oh, and then home cog, home emo, and miss. So we've got quite a few variables, not like tons, but a decent number. But the main point is we've got this anti-1, anti-2, anti-3, anti-4, and read 1 to read 4. And we want to measure this, we want to basically look at change over time, right? So this is a within subjects design. So we can't specify multiple outcomes. We can't say the outcome is read 1, read 2, read 3, read 4. So what do? We make the data longer. Okay? So this is an example where we have essentially the exact same sort of thing we have now. We have 1999 and 2000, and we have all of these observations. And what we're going to do is we're going to move the names of those columns into their own column called year. Okay, so year just repeats 1999, 2000, 1999, 2000. And then each of these observations just basically get flipped. Okay, so these all go into a second column. So the simplest case, and most of the time, the way that we will be working with this is you can think of the names of the columns going into one new column, and the values from those columns going into a second new column. Okay, so you have, say, 10 columns, and they're going to be reduced to 2 columns. Or you have 6 columns, they're still going to be reduced to 2 columns. Okay, so it almost never matters how many columns you have, it's generally going to be reduced to 2 columns. There's more complicated things we can do from there to expand it out, and we'll talk about that more. But that's sort of the starting point, right? We're taking a bunch of columns and we're reducing them down to 2 columns. One column that has the old names and one column that has the old values. Okay, so let's try this. We're going to start with an easier example because this is a little bit complicated. We're going to start with just the reading data. Okay, so there's lots of ways we can do this, but I'm going to take Curran and I'm going to say select ID and any column that starts with read. Okay, so go ahead and run that. Sorry, I have a hard time checking the chat. I will try to be better about that. I have that window open now, but glad you got it figured out, Manuel. And thanks for checking, Chris. Okay, were we successful there? Okay. Seems like most people were. Sean, I want to check in with you. How are you doing?
Yeah, this is all new, so I am struggling along, but don't worry, I'll figure it out.
Okay. All right. Yeah. So this is, if you don't have a lot of experience with R, this is definitely challenging. But you can see now, after just running this select code, which is from dplyr, we now have just these columns. So we have ID and just the columns that start with read. So what should our data look like? What I want you to do is, I'm just going to set the timer for 2 minutes. This is what our data look like currently. I want you to you can try it if you know what the code should be already, or if not, just sort of visualize, try to think about what our data should look like now. Looking back to that old slide where I showed you the move into 2 columns, think of what it should look like, okay? Who wants to volunteer? What should these data look like?
Yeah, so for example, ID 22 should have, or ID 34 should have like 4 rows, and within each row, it's like a time period. So instead of just having 1 row per ID, you'd have like multiple rows per ID.
Good.
And you only have 2 columns. That's the read score.
Good. So you would have 2 columns for the data, but you would also have your ID column. So you would end up with 3 columns. You'd have your ID, and then a column that stores the time point. So whether it's 1, 2, 3, or 4, and then you'd have a column for the score, right? So that's how the data are going to move. We're going to say, okay, forget about ID. we're going to take the rest of these columns and we're going to move them into 2 columns. One that has the old column names, so it's going to go read 1, read 2, read 3, read 4, and then one that has the old values. So for ID 21, it'll go 2.1, 3.9, NA, NA. Okay, so that's what we're going to do. All right, and the way that we do this through the tidyverse is through a function called pivot longer. Okay, and so we have our data wide, we're going to pivot it to move it longer. Okay, the initial draft of this function was called pivot long, and actually on Twitter, Hadley solicited feedback and somebody said longer might be better, and I think that's a significant improvement because you'll hear people talk very often about long data and wide data. The problem is that's a lot more ambiguous because long data can often become longer even if you want it to, right? And wide data can still become wider. So it's not like there's a specific format for long data and a specific format for wide data. So pivot longer means we're just taking whatever it is and we're making it in a longer format, so more rows than it had before and fewer columns, okay? And so what we do with this is we say pivot longer. So first we're going to pipe to it, right? So that the first argument of this is technically the data. But then we'll say the columns that we want to include in this pivot longer is read 1 to read 4. So all of those read columns. Okay, we could also do starts with read, just like we did during the select, or we could do minus ID. So include all the columns except ID.
Hey,
Then
Daniel.
we'll say, yep.
Sorry to interrupt your flow there, but I gotta check. As I was trying to build this pivot longer, I totally messed up the columns piece. When you grab specific columns, is it sequential? So like you go read 1 and then after the colon, whichever column you put next is gonna grab everything between those, or is it because it's ordered? Yeah, okay.
Yeah, so that's, yes. So when you use the colon, let's go back here. When you use the colon, it's going to grab the column read 1 and every other column until that next column that you supply, which is read 4. So in this case, that's what we want. But if we had some other columns in here, like maybe some other ID variables or whatever, we would not want to use the colon like that, okay? So another way you can do this is with C. So you could say C, read 1, colon, read 4, comma, anti-1, colon, anti-4, or something like that. But you can also specify it in a bunch of other ways. So as I mentioned, you can use, just like we did here, starts with read. We could also use exactly that same code as to specify the columns. And similarly, I think I actually have an example of this. We can also say minus ID. So you can say include all the columns except this one, or except these, by using the minus. And otherwise, you're saying from this one to this one, include all of those columns. Okay? So we're taking those 4 columns in this case, and we're saying we're going to include all of those as we pivot longer. And the names from those columns are going to go to a new column that we're going to call time point. Okay? This is up to you. You could call it whatever you wanted. So you could call it wave, you could call it time point, you could call it whatever, anything that makes sense to you, right? And then the values from those columns are going to go to their own new column, which I'm calling score, but you could call, recognition or read recognition or whatever, anything you want. So these 2 values are completely up to you. They just have to be something that's interpretable to you. But basically, whatever columns you put in here are going to move to 2 new columns. The names 2, 1 is going to be the column that has the old names, and the values 2, 1 is going to be the one that has the old values. Okay, questions on that?
If you have other like time invariant variables in this data set, would they just still be included and just be like, if it's, somebody's a 1 on something, it'll just be 1 across all of the rows?
Yes. So if we had, basically if we had person level variables here, like let's say we had a gender identifier, right? Then we would still, when we're doing this, we would only put the columns in here that we want to include in that pivot longer, that we want to make change their format. And then the gender column would just stay constant. So for one given student, it might say female, 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 female. Does that make
Got it.
sense? Other questions? Okay, we will do more of this too. So as I mentioned, you can also specify the columns not to be included in the pivot. So you can say minus ID. You could also say minus C and then specify a bunch of columns. So minus all of these columns, don't include any of these columns. Okay. And then the question is, are we done? All right, so this is what our data set looks like. And let's say we're not interested in antisocial skills at this point, and we want to actually fit like a growth model just to this, like an unconditional growth model to the reading scores. Are we ready to go? Can we model this starting right now?
Do you have to deal with the NAs?
We do have to deal with the NAs, but actually we can handle that during the modeling. So we're okay with that for the data structure, but there is something else we have to do here.
Time points.
Time points, exactly. So what do we need to do there, Asha?
We need to, I don't know the right word, but there are 3 different ways of coding the time points, like from beginning, midpoint, or endpoint. So here, whichever we can choose from 0 to 4 or midpoint, or the endpoint from 4 to or 3 to 0, something like that.
Yes. So you're talking about centering basically. And so centering is just like, where do we want our 0 point to be in this time? And so like very often if you have like say an interrupted time series design where you have an intervention being delivered at a specific point, you might want to center your time right there at the, like when the intervention starts. In this case, I'm just going to assume that we want our intercept to be at the first time point, right? So what kids were when they started. So what we need to do here though is we need to take our time point, which you can see it says CHR, right? So that means it's a character column. And we need that to be numeric, right? We need to be able to model that as a number. And so what we want to do is change this from read 1, read 2, read 3, read 4. So it's probably 0, 1, 2, 3. Okay, and then 0 will represent our intercept, which would represent our initial, the initial reading recognition scores for students. And then from there, it would be by wave, whatever wave represents. Okay, so we probably want to fit a growth model. Time point needs to be numeric. There's a bunch of different ways to do this, okay? So this is like everything in coding, basically. There's not a way to do it. So I'm going to show you a bunch of different ways, well, a few different ways. And there are still plenty of other options, all right? But these are just a few, okay? One that's pretty easy is we could just parse number, okay? So from the readr package, there's this parse number function, and it's super nice because what it does is it'll just look at a string and it will find the number from it. It will pull that number out and then it will convert it to numeric. Okay, so I'm saying parse number on time point and then I subtract 1. Why did I subtract 1? Well, I already said that because that's where I want the intercept to be. If I didn't subtract 1, my model would actually still fit and it would be the exact same thing, but my intercept would be totally uninterpretable because it would represent the average score at the -1 time point, right? Because if you think about a growth model, right, it's just a line. And so all we're doing is changing the intercept is just like, what's our reference along that line? And so we can extend that line into impossible areas like the -1 time point. And the model would actually fit and it would be fine, but we wouldn't be able to interpret our intercept, okay? So that's why we make 0 an interpretable point in the data, okay? So this is all now the same thing. I go read, I pivot longer, just like we did before, and then I pipe that straight to mutate, and I'm creating a new column here, which is actually overwriting a column because I already have it there, which is going to be the parse number version of time point -1. Okay. Questions?
Hey, DA, I fought with this for a while. I think because I didn't put inside my mutate, I didn't put, I had time point in quotations. Can you just give me, is that because it's piped there? It already knows the data frame?
Yeah, so you had time point here in quotes, right? Yeah, so this is like an area where the tidyverse makes things easier for the most part, but every once in a while it's confusing because this is a new column name, and so therefore it has to be a string, all right? But the vast majority of the time you're working with anything in the tidyverse, you will just give the bare column name like this. In this case, we're saying this is a new column name, and so that's why it has to be a string. But in the vast majority of cases, you just give the bare column name like that, and it'll grab it. And if you give it the string, it will not work for you.
I was wondering if you have any suggestions on how to use this mutate option when the time point variable is a string but doesn't have like like a numbers attached to it. So if it's like December, January, February, March, what would your approach be in kind of recoding this using this mutate?
Yeah, so mutate is like a general function that is meant to either create or overwrite existing columns. And what you put in there is going to vary to a huge degree because it just depends on what you want to do, right? But that's generally what you want to do is, well, not generally. That is what mutate is for, is to create new columns and or overwrite existing columns, okay? And so if, like, say you had month and you wanted to create data from there, one thing you could do is convert it first to an R date, right? So R has a date class, and you could convert them to a date. And even if you don't have the days in that month, you could just say, okay, well, they're all from this year, and it would just put it as the first day for each of those months. And then from there, you could even use like a different function, like the month function from Lubridate, and it would pull out like this is the 7th month, and this is the 3rd month, and this is the whatever. But unfortunately, that's one of those questions where it's like so broad, it's impossible to give like a super general solution that's going to work for everything because it's going to really depend on the data and what you're trying to do. Other questions?
Dan, what I've done in SPSS, and so this, I'm coming from that mindset, like I've done a lot of recodes, and so like manually recoding and assigning values, I'm guessing most ways are going to be easier in R, and that you can, like parse number is dramatically easier than recoding individual values if you have especially a lot of variables that you're playing with. But is that kind of the approach that you're talking about? Like you can do that?
Yep, you can absolutely do that. So there's, if you're going to recode sort of more manually like that, which is still something you have to do fairly regularly, there's sort of 2 main functions that you'll want to use. One is just if else. So it's if some condition is true, then do this thing, otherwise do this other thing. And that's great if you have like a specific, like a really, like let's say you have a column that's treatment and control, and it's like TRT and CTR, whatever. And you could just change it to a factor, but let's say you wanted to actually plot it and you wanted it to say treatment, not TRT. Then you would say if else, whatever the treatment column is, equal, and then in quotes TRT, comma, so that what would happen if that's true, and then you'd put in quotes treatment, and then you'd put comma, and then what would happen if that's not true, and you would say control, right? So that's like one way to do it. But if you have more than that, like let's say you have a gender column that has male, female, non-binary, and they're like currently at 0, 1, 2 or something like that. Then you could use case underscore when, and you would say when gender equals 0, and then a little tilde male. When gender equal 1, tilde female. And then the last one would be true, like what's the default condition, and then you'd say non-binary. Right, so there's a lot of different ways to do that kind of stuff too, but that's generally. Okay, another way that we can do this same sort of thing. Okay, so this is doing this through a new function. So we have pivot longer, where we're moving it to this longer format, and then we're piping that to mutate, and we're creating we're overriding the column through mutate. Another way that we can do this is just by actually transforming it during the pivot longer, okay? And there's a couple of ways that we can do this, but this is probably the easiest or one of the better ways to do this. Okay, so we have read, all of this stuff up here is just the same, but then we have names to time point, and then we have this additional argument, names transform, okay? So I'm going to conduct a transformation to that names column, that time point column that I created up above. And what I'm going to do is I'm going to take time point and I'm going to say parse number. So that's going to apply that function to it immediately after it does the pivot longer. And then we get something like this. Notice this doesn't have the -1 though, so we would either have to pass it to mutate from there, or we could make this function a little more general. And that's what this does. Okay, so and you could actually put exactly this down here where this is, but this just breaks it out a little bit more explicit. So I've created this little function called sub1, which is a function that takes a generic argument x, and it says, okay, parse the number in x and then subtract 1. So that's what that function does. Okay, and then in this part, I'm just saying names transform list time point equals sub1. Okay, so that's going to apply that sub1 function I created up here to the time point column. All right, those versions are maybe a little bit more complicated, and so don't worry about them if that feels weird or whatever. This is probably more natural, and if that's how you want to do it, that's completely fine, right? There's nothing wrong with that. I just wanted to show you some alternatives as well. Okay, here's one other way that we could do this, sort of. Although it doesn't seem like it worked. Oh, yeah, no, it didn't work. It almost worked. So there's this names prefix one that you can do. I don't know why this didn't work. I swear it did work when I was doing it. But names prefix, right? So this said read 1, read 2, read 3. So with names prefix, I can say here's the prefix for each, for that names column, and it will just pull that off as it does the pivot longer. And then names p type, this should work. I'm not sure why it didn't, but this is saying now take the time point column and change it to numeric. So, but you can see it's still character, so. And you would still have to subtract 1, so that's less than ideal anyway. All right, so questions on that before we move forward? Okay, so moving longer is super useful for multi-level modeling, and that's usually what we're going to have to do. Occasionally, we will also need to move wider. Okay, so you have it in this long format, and you want to move wider. So sometimes this is because you want to join data and you need to have unique like keys for the data. So what we're going to do is first just create the longer data. Okay, so you should already have this done, but just store it in an object. I've called mine L. You could call yours L or LNG or whatever, something to specify that this is the longer version of the data. Okay. Then we're going to move it back out wider. Okay. And so what I've done here is I've said L, this is my longer data object, and I'm going to pipe that to pivot wider. So instead of moving to a longer format, we're moving to a wider format. And I'm going to say the names from equals time point. And notice I don't have to use the quotes here, right? That's only in pivot longer. And really, you should probably just think of it like that. Like generally, you're going to supply bare column names except for pivot longer, because that's just about the only exception in the tidyverse. So the names are going to come from that column time point. Okay, so let me look back here. This is my time point column. For every unique value that I have within time point, I'm going to get a new column. Okay, so I have 0, 1, 2, 3, 4 different unique values, and I'm going to get a column for each of those. And then the values for those columns are going to come from score. Okay, and then I end up with a data set that looks just like this. So this is just doing the exact opposite of what we just did. Instead of moving to a longer format, we're moving to a wider format. Clear? Questions?
When you know you're going to be like moving around between the two, do you just generally tend to create two objects so that you can more easily sort of access and change them when you need? Like you'd have just wide and long, or is that just sort of not always necessary?
Yeah, so if I knew that I needed both for, maybe I need one for plotting and then one for analysis or something like that, then yes, I would have two objects that I'd be working with. But very regularly, as I'll show here in just a second, it's actually super useful to go to a longer version of the file than you actually need, and then to go wider from there to not replicate what you had, but to get actually a new structure again. Okay, and that's how we will get a column for anti and a column for read from these data, both corresponding to the specific time point. But yeah, like organizational stuff with R is a little bit tricky, sort of because you don't want to end up like polluting your environment with 18 million objects, but you also don't want to have to recreate objects a bunch of times either. So yeah, I don't know that I have super good advice there. But.
No, that's perfect. I generally, out of anxiety, just save a lot of objects, and then I end up having to redo. So it's just nice to know what's best starting.
Yeah, and I probably do the opposite, where I have like 3 objects, and then I do have to redo things sometimes. And that's particularly problematic when one of the lines of code takes a long time to run. So yeah. Okay, here's a challenge for you for 6 minutes. What I'd like you to do is take the full current data now, not the subset that we were working with before, and try to move the data so that it looks like this. So notice I have this column variable that looks like this: anti, 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 read, 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 time point, which is 0, 1, 2, 3, and then the score or whatever. Okay, so 6 minutes. Give it a try. If you're not successful, that's fine. Don't worry about it. Don't stress about it. But see if you can do it. Okay. Okay, so it looks like about half of you got done. If you did not get done, please do not feel discouraged. It's totally fine. This is new. So I will come over here. Let me switch my share and I'll show you how I would do it. Okay. Oops. All right. So here, let me get back over here so I know what I'm doing. So I have current, right? And I'm going to pivot longer. And I'm going to say the columns that I want starts with either read, or it starts with, actually, Let me see here. I think I had to say C. Starts with anti. Okay. I think that works. Let me just make sure. Yeah. Okay. And then I'll say names to. The other way we could do this, right, is just say anti1 to read1 or whatever. Names to variable, and then values to score. Okay, so that gets me part of the way there. All right, and then from there, I'll just say mutate time point is equal to parse number on variable. Okay, and I get something that looks like that. So then I want to probably just do -1. Okay, so that gets me most of the way there. The only problem is we still have the number on the end here. Okay, and that is tricky, and we didn't talk about how to do that. So I'll show you one way. There are, again, lots of ways we could do this, but I'll say variable is equal to, from stringer, string sub variable, and I'll say -1. Let's see, what does that do? That's exactly the opposite of what I want to do. I want to say 1, let's see if this works. 1, 2, -1? No. Okay. So we'll say 1, 2, 1, 2, 3, 4. 1 to 4. Let's see what that does. Nope. Read. Oh, that's really weird. What is that doing? Is it grouped or something? I'm forgetting how I did this now. So I know how I would actually do it, which it would be to say, well, let's just do it like this. String, substring, 1 to 4 variable. Let's see what that does. Nothing. Okay. Apparently I've forgotten how I did this, which is a little embarrassing. 1, 2, 3, 4. Let me look at substring real quick. Start, stop, yeah. Oh, yeah, X. Okay, so I have them backwards. 1 to 4. Arguments, oh, I need them as separate arguments. That's what it is. Okay, so substring 1 to 4, or how I was trying to do it to start, would be variable is equal to stringer, string sub variable 1 0 4 variable. Did I spelled something wrong there apparently? String sub. Oh, I need to do that. Okay, that works also. Okay, so that's a couple of different ways that we could get at that. That's still not, I don't think, the way that I did it originally, but that's okay. All right, so either of those would work. There's also ways that you can look for digits in strings, and I think that actually is the way that I did it originally. So you would go like this, like let's just call it test. And then you would say grepl. So grep is like a search function, and grepl is like a logical function. And so let me get rid of this. Well, that's not going to be that helpful. So I'll say grep variable, and then you just so --d, and that's actually this. All right, so we're looking for D, and we're going to replace it with nothing in variable. Maybe. Okay, whatever. I'm gonna abandon this. So that's a couple of different ways that we could do it anyway. We got there. It was a little bit more of a struggle than I expected, but we got there. All right. So if you didn't get this part in particular, obviously I struggled with that way more than I anticipated, then that's totally fine. But hopefully you got at least to this part. Okay. Did most people get that far? Okay, good. All right, then the next thing is, once we get to this point, this is still probably not actually what we want, right? Because what we really probably actually want is to have a column for read and a column for anti, okay? And so what we do is we can just go ahead and pipe straight from here and say pivot wider, where the names are going to come from variable, and the variable and the values are from score. Okay, so now because we've taken off that number here on variable, this will now just give us two new columns, which will be read and anti, and we've got this time point column already, so that will then give us finally the structure we want, 0, 1, 2, 3 for their reading score and for their anti-score. So that should give us now, let me make this a little bit wider so we can see it. That gives us now finally what we were looking for. So we can see their reading and anti-scores are paired up for every time point, and we have the ID repeating. These other variables are all time invariant. So they are person level variables, and so they just get repeated as well. Okay, and up here, again, I surrounded these with C, but we could have just done like something like this too, where we'd say anti 1, 2, read 4. That should give us the same thing. Yeah. Okay, so this is now a fairly complicated data munging task, right? We have this data set that's in a pretty wide format. We're going to first put it in a longer than we actually want format, parse the number from there, clean up the name so we remove the number from there, and then we can now pivot wider using that cleaned up names version to get the final structure that we actually want. Okay, questions on that? I was going to make that a challenge too, but we're running short on time. So, all right, I'm going to run through just a couple more examples. You don't have to follow along here. I'm just going to show them. Okay, so this is this LS19 data. It's letter sounds data collected from the state. And so this is actually just school level data. So we're not going to do this, but well, I had more challenges, but it is 10:30, so we're going to move on. In fact, let's just go ahead and take a break for now, so we can come back to this later if you're still having questions about this stuff, and I can walk through it with you. But as a class, let's take 5 minutes and then a 5-minute break, and then we'll come back and we'll talk about modeling. And then if we happen to have time again before the lab, like if we end up, you know, going through the modeling in 30 minutes or whatever, then we can always go back to that. Does that work? So we are going to talk about modeling now. And as Brock said, we're going to go back to the current data in the form that we just had it. You could actually use the form that you had before too, though, because I don't think I'm actually ever using the anti variable. So either one is fine. We'll just be using the read variable. Okay, so we're going to talk about random intercepts model, random slopes model, and some of the complexities involved there. We'll also talk about unconditional model. Okay, so we're going to start with an unconditional growth model. And I think I mentioned this before, but I am going to try to build in more examples of like more non-growth model examples, because that tends to just be my bias. That's like where I use this modeling framework the most. But that is sort of where we're getting started today, because that happens to be what the data set is. And that's kind of going to be there throughout a lot of the slides, but I'm going to try to start to make that less the case. Okay, so model fitting. We could start with a fully unconditional model entirely, but so not unconditional growth model, but just an unconditional model. But that's actually, in this case, I would argue a misspecification, because we know coming into this that we have a within person design, and so we want to estimate something more than just a mean for each student across those time points, right? We want to estimate a slope across time. So slope is going to be, time is going to be an important predictor in this case, okay? So because we know theoretically that that's going to be a really important predictor, starting with just an unconditional model, I would argue is actually kind of like a straw man and not really even worth doing. So unconditional growth model, on the other hand, is probably a great starting point. So we're going to first start with fitting a model with just random intercepts. Okay, so that's going to be, we're accounting for time, so we're fitting a slope for time, for growth, but we're going to give each student their own starting point. So everybody can start wherever the data says that they start, but the model is going to force them to all grow at the same rate. Okay, so this is what the data look like. Hopefully you have data that look similar to that, if not exactly like that. All right, so we're going to first start with fitting the model. So you can copy this code, you know, click the button there, copy, bring it over, or you can write it yourself. But please do run this, okay? So we're first going to load the LME4 package, and you will see when you do this on your own that this also will spit out some messages about loading like the matrix package and other things. So it's loading other packages for you. Then we're creating a new object. I'm calling this M-intercepts, okay? Typically, I would actually call this like M0 as like my baseline model, which tends to be my convention, but I'm trying to make it really explicit here that this is the random intercepts model, okay? When we are fitting a model to data that we are at least assuming is continuous, which is the case with read, then we're going to use this Elmer function, okay? Elmer stands for linear mixed effects regression. So I mentioned in the first class that multi-level modeling goes by a bunch of different names. Mixed effects modeling is the name that is used most in like statistics circles, and it's used in a lot of other areas too, but that's where Elmer gets its name, okay? Linear mixed effects regression. Then we're going to say read is the outcome, so our column that says read for every student, and then we have a tilde here, okay? So this is saying this is the outcome, and it's modeled by all of this stuff, okay? So we're going to say 1, meaning an intercept. It's modeled by an intercept plus time point, our time point column, okay? So time point is a predictor of read. Then we're going to say plus, and we have parentheses here. The parentheses specify our random effects, okay? So here we're saying 1, meaning our intercept, varies randomly across ID. Okay, so we have this ID column, which is every student, and we're saying 1, meaning the intercept, varies randomly across ID. Okay, so every ID has their own intercept. And then we just specify the data equals D. Okay, any questions on that? All right, so that's our model. That's our random intercepts model. I want to talk just a little bit about what this looks like in notation. Okay, so in week 4, we will talk quite a bit more about different notation. But this is the notation that I'm expecting most of you are familiar with, the Raudenbush and Breich notation. Okay, so this would say reading at time point I for student J is modeled by an intercept plus time point at level 1, and then some residual error variance. okay? Each of these parameters then get their own equation. So pi 0 jk is equal to beta 0 0k. So this is the actual fixed effect for the intercept here. So this is like the average intercept plus FRL. Oh, I don't have FRL in the model though. So this would be a more complicated model than what we're currently doing. But this would be a student level predictor of the intercept. All right. So the intercept is randomly varying. That's what that R0 JK says. But the slope is not. So we don't have a plus R1 JK down here. Okay. In the Gelman and Hill notation, this is actually what we're fitting, not this one. It would look like this. And so again, I'm going to talk about this a lot more as we move forward. So this is sort of just a preview. But this is the same model as this if we took out this FRL part, which is just a typo on my part. And this is saying the ith reading point is assumed generated from a normal distribution that has this mean structure. Okay, the mean structure is just saying alpha, meaning our intercept, j. Okay, so every student has their own intercept plus time point. Okay, so time point is going into the mean structure. So there's a different mean for every time point, basically, for every student. And then that has some constant variance, which is the same as this, basically. And then alpha j, our random intercepts, are also assumed generated from a random normal distribution that has a mean specified according to the mean intercept. Okay, so this is basically the same as this up here. And then this has its own variance, which is different from the person level variance. Okay, and that distribution is assumed for ID j equals 1 to j. Okay, if that's not super clear, that's okay. We're going to be talking about that more, but that's the notation we're going to be moving towards. Okay. All right, so what does this model look like? I realize I'm not echoing the code here. We will get to that next week. Next week is when we're going to talk about plotting the results from models. But I still want to show what it looks like here anyway. Okay, so below it is a random sample of model predictions. So what the model is predicting for 20 participants. So I've just randomly selected, or I think randomly selected 20 participants and shown what the model looks like. So you can see there is quite a bit of difference in what the model is predicting these students' intercept will be, where they start, but the slope is constrained to be the same across all students, right? So every student has the same slope, even though the intercept is different for all students. Okay, so had we fit a standard regression model instead of a multi-level model, we would have had one slope. That's it, just one slope, which we would have assumed represented all students. Okay, all kids, whatever. I don't know if they're students or kids or whatever. But in this case, we get separate lines for every student. The only thing that changes is the initial starting point. Okay, so now we're allowing each participant to have a different starting point, but the rate of change is assumed constant. So then we might think, how reasonable is this assumption? And this is a hard question. It's harder than it initially sounds like, because you typically, like just logically, right, would think, well, every kid's going to start at a different place and every kid's going to grow at a different rate, right? They're going to learn at different rates, whatever. Every kid's unique. They're all different. So we would probably not want to make this assumption that they're all progressing at the same rate. The challenge is that even if that is theoretically true, your data might not be sensitive enough to pick up on those differences between participants in terms of the rate at which they're growing. And so actually assuming a constant rate of change for all participants might be the most reasonable, parsimonious modeling option, okay? Because the variance, like the differences in those slopes might be so tiny that it's better represented just by a single slope. Okay, so let's look at this a little bit deeper though. So here's a random sample of 9 participants, okay? And again, I'm not echoing the code. We will get to these plots next week, okay? On the y-axis, I have the prediction, the model prediction. And then on the x-axis is the time point, 0, 1, 2, 3. And you can see the blue line represents what the model is predicting, and those points represent the observed score for each student, okay? So this is a random sample of 9 students. Here's a different random sample of 9 students. And I would say that this is looking pretty good. So basically just changing the intercept is getting you a lot better predictions for these students than you would get if you just fit a single regression line. Okay. So this is all what I mentioned. If you want to look at the source code for these slides to see how I created those plots, that's available to you in the GitHub repo. But we will talk about that next week, so don't worry about it too much. Okay, moving on from that, this is actually probably where I would usually start right after fitting the model, and then I'd probably do that other stuff after. Right after fitting the model, I would run summary on the model, okay? So summary on m-intercepts, that's going to get us this output. From here, not always, but most of the time from here on out, I will not use summary. I will use a function from the ARM package called display. And that's not because I think display is better. It's because it's more compact. And as you can see, this is a pretty simple model, right? We only have a random intercept and we have one predictor. And it's still actually not fitting on the slides with only that on there. So that's why after this, I'll move to ARM display. But I wanted to show you this because A, it does basically fit on the slides, and B, this is how I actually typically do it. Okay, but all the same information should be repeated in both of them that you want. Okay, so you can use ARM display also if you want. But basically when we're doing this, the first thing that it's going to show is just, it's going to echo the model that we fit up here and the data that we fit it to. And then it's going to give us the criterion at which it converged, which is fine. Don't really care about that unless we get convergence warnings. Scaled residuals, I again usually don't care about those too much unless I'm doing model diagnostic stuff and I care about like maybe outlier sort of things. But this is really where we're getting down to the model results. Okay, so we have the random effects and the fixed effects, and these are kind of in opposite order of the way that I think of them. And actually, if you use ARM display, they do show up in the other order, because the fixed effects are sort of generally where I would start. Okay, so the intercept is going to represent just like regression, right? It's going to represent the value when the predictor is 0, the average across the sample when the predictor is 0. So the predictor is time point, right? And so 0 represents their initial time point. So this says that kids on average had a reading recognition score of 2.7 when they started in this study. Okay, so their initial reading recognition at the first time point where they started was 2.7. Okay, they grew on average or progressed on average about 1.1 points on that reading recognition thing per time point. And that's hard in this case because I don't really know what time point represents. When we talk about growth models a bit more, we'll talk about putting this in different scales. So you could have this be per year or per season or per month or per week or whatever. And that often makes it more interpretable, okay? In this case, it's 1.1 points per time point. And I don't really know what a time point represents. That's it. That's what we got, okay? Up here are the random effects. And we get a little bit of additional summary information here too. So we have 1,325 observations. And we have this group, which is ID, and we have 405 of them. So basically we have 405 participants, and across those 405 participants, we have 1,325 observations, okay? So these are the variances for our two variances in our model, our residual variance, like everything that's left over, and our random intercept variance, okay? I tend to not look at the variances in terms of interpreting the model. You'll use those if you're doing things like calculating the ICC or whatever. There's lots of reasons that you would use those things. But in terms of interpreting them, standard deviations are generally much more interpretable, right? And these are related to your fixed effects. So we say, for example, for the intercept, because we only have a random intercept, students began with a score of 2.7 points on average, and that score of 2.7 varied between students with a standard deviation of 0.88. Okay, that's how I would always interpret this. Look at the fixed effect, interpret the fixed effect, and then talk about the variation in that parameter across units, whatever unit that is. Okay, and then the residual variance is basically what's left over. So you could say basically our model predictions were off by a standard deviation of 0.67, essentially, right? It's like the distribution around the distribution of your errors has a standard deviation of 0.67. All right. The other thing is I didn't know that this got loaded. It shouldn't have. So I have some error in my slides there. It must have loaded it earlier. Generally, you will not have the degrees of freedom, t-value, and p-value here because basically there's not a good way to estimate the denominator degrees of freedom unless you make really strong assumptions, which is what this Satterthwaite method does. That Satterthwaite method is actually really well accepted, even though people like Douglas Bates, who wrote LME4, thinks it's baloney. So you can use it and you get these t-values and p-values, but typically you will get t-values, but not degrees of freedom or p-values, unless you load this other library, which I'll show you here in a little bit. Okay, before we move on to random slopes, are there any questions on that? Okay. Does this feel sort of like review-ish? Okay. All right, moving on to random slopes now. Now let's fit a second model that not only allows the intercept to vary across students, but allows the slope to vary across students. So again, coming back here to our model output, we say that students started on average with a score of 2.7 points, and that varied between students with a standard deviation of 0.88, but we're assuming all students grew at 1.1 points per time point, right? There's no student level variation in that slope. So that's what we're going to do now, is we're going to model the variation in the slope in addition to the variation in the intercept, okay? And we do that like this. So here I have Elmer, all of this fixed effects part is the same as before, but now I'm saying 1 plus time point is randomly varying across IDs, okay? So just a tiny bit of change to say that I want not only the intercept, but also time point to randomly vary across IDs, okay? So quick note on syntax, I'm being super explicit in the above syntax to say, here's the intercept fixed effect, and the intercept is varying randomly across IDs. Typically, I would not be that explicit, okay? I would probably actually write it like this. Read is modeled by time point plus time point varying across IDs. This is the exact same thing. So if you don't put the intercept in there explicitly, it's assumed that it's in there, okay? You can omit the intercept if you want also by putting a 0. So you could say 0 plus time point, and then plus 0 plus time point in the random effects or whatever also. But if you just put it like this, it's going to be assumed. You could also have it where you'd say read is modeled by time point plus 1 ID. Okay, so then that would be a random intercept model, but you don't have to have the 1 on the left side just to have 1 in here. Okay. All right. Another important point here, though, is that you are not only estimating the additional variance of the slope, you are also estimating the covariance between the intercept and the slope. Okay. And this is part of why I prefer the Gelman and Hill notation, is because it makes that very explicit. You're not only estimating the variance in the intercept and the variance in the slope, you're also estimating the covariance between them. Okay, and otherwise this is the same. So this is now saying we have the intercept and the slope, so you can see both of these are randomly varying by looking at the subscripts, and then these are assumed generated from this bivariate normal distribution with a mean for each of them, which is the fixed effects, and then this covariance structure. Okay. So if we look, I don't know why that FRL is in there again, but if we look at the, if we look at this version, the Gelman and, or the Raudenbush and Breich version, all we do is just add this R1JK, right? That's the only difference between this notation and the last one. And so it's clear that you're estimating an additional variance, but it's not so clear that you're estimating an additional covariance, whereas this makes that much more clear. Okay. You could add an additional line where you're stating the distributional assumptions of your random effects, which is what they typically do. But then you might as well just go to Gelman and Hill at that point, because then it's also, you know, the Raudenbush and Breich notation can just explode. Like you can have, if you get to like 3 or 4 level models with a bunch of different predictors, you end up with an equation that's literally like pages long sometimes. And especially if you're trying to show the distributional assumptions like that. And so, yeah. Okay, same 20 participants from before. And now you can see that the slope, the slope of the line does differ across students. So we can visually look at this and say, okay, does that seem like it's worth it? And it's hard to know, right? But you can see that there's quite a bit of, there is definitely some differences there, right? There's the lines on like overall generally are still basically trending in the same direction, but there's also quite a few instances of lines crossing, right? So that does give us some evidence that the model is estimating that students are actually progressing at different rates. How much different is hard to know, and if that variation is really worth modeling, we can't tell from just looking at this, but this is just a sort of quick visual. All right. We could also do this same thing where we're looking at those same 9 participants, and that looks good. It looked pretty good before too, though, and that looks good also. So let's look at the output. Again, this output is going to be slightly different than yours because I have this other package loaded, but it's basically the same. Okay, so again, I would come basically straight down here to the fixed effects. The fixed effects are pretty similar to what they were before, but now we have this additional variance here. And you can see we have the correlation estimated there also. Okay, so students started on average with a score of about 2.7 points. That varied between students with a standard deviation of about 0.75 points. And they grew on average about 1.1 points per time point. And that varied between students with a standard deviation of about 0.27 points. Okay. Questions? All right. We've kind of already done that. The only thing I want to do here is also talk about the correlation a little bit. So in this case, we have a pretty modest but positive correlation. Okay, so the correlation between the intercept and the slope, I think, is generally more interpretable when you're fitting a growth model than it is other types of models. But basically, because the correlation is positive, even though it's modest, that means that students who are starting higher are having higher growth. and students who are starting lower are having lower growth, right? If that correlation was negative, which is fairly common that we see with growth models, then your interpretation would be the exact opposite. Students who start higher have lower growth, and students who start lower have higher growth. Okay, and in this case, the correlation is fairly low, so you would want to be a little cautious about interpreting that, but there is a small positive correlation between the intercept and the slope. Okay, and that sort of thing for education anyway can often have important implications. So specifically, if you have a negative slope, that might just imply that your intervention or whatever is helping kids that are behind catch up at a faster rate than they would have otherwise, or something like that, right?
Hey, Daniel, on our output, I mean, at least on my output here, I have just the correlation of the fixed effects, and it has like a negative 0.4 on the same data. Does that seem?
Yeah, the fixed effects correlations I would not really worry about. This is the fixed effects of the correlation of the random effects is more easily interpretable. But yeah, I would probably just ignore those fixed effects correlations unless there's sort of reasons you need to dig into it, which would probably be more like if you're having model fitting problems. Okay, other questions? Okay, so in equation form, it's going to end up looking like this. Okay, so we have our reading scores are assumed generated from a normal distribution that has a mean of 2.7 for each alpha, okay, plus 1.12 for each beta. Okay, so this is actually a bunch of them. And then the with a standard deviation of 0.59. Okay, and then these two are assumed generated from a normal distribution with means of 0, and then these standard deviations in that correlation. Okay, so the other reason I like this syntax or this notation is that it actually helps show the assumptions of the model, I think, a little bit more clearly. So you can see very clearly there that we're assuming the data are generated from normal distributions. And if our data are actually not, which most of the time they are, that's a pretty safe assumption. But if they actually aren't, then that might lead to problems. Okay. Later in the term, I think it's like week 7 or something like that, we will actually talk about simulating data, assuming a multi-level model generated the data. Okay, and so then we would take basically an equation just like this, and we would simulate data from that equation. Okay, p-values. Unfortunately, my slides showed them earlier. Douglas Bates, as I mentioned, believes they are fundamentally flawed. This is a link to a frequently asked question, or no, it was our mailing list related to mixed effects, where he talks about it more in depth as why he does not include that. So if you want them, then you can get them through this Elmer test package. The other thing is I sent out through the announcement a link to the mixed models FAQ, and that also talks about this same issue. That's by Ben Volker, who's also an author on LME4, but he basically just summarizes Douglas Bates' problems with it, and it's a little bit more accessible, I think, than Douglas Bates, who's very smart, but hard to understand sometimes. Okay, so alternatives. There's basically two ways to approach this, right? One is to not use p-values and instead just interpret the confidence intervals. That is actually generally my approach when I'm using this package when I'm using multi-level modeling for publications. if your reviewers don't like that, or you don't like that, you can get the same p-values that other software reports by using the Elmer test package. Okay. So confidence intervals, real quick. We'll talk about these, and then we'll talk about Elmer test package for a minute. Confidence intervals are computationally intensive. So there's a couple of different options. By default, it's going to do what are called profiled confidence intervals, which basically means it's going to go through the fitting process again, but it's going to monitor those parameters as it goes through, and it's going to find sort of the lower and upper bounds for whatever range you specify. By default, it's the lower 2.5 and the upper 97.5, so a 95% confidence interval. And it's going to do that through the fitting process. One of the things that's interesting about profiled confidence intervals is that they do not have to be, it does not assume that they are symmetric. Okay, so you could have a confidence interval that goes like, and it's not super common, right? But like, let's say your fixed effect is 12, and then you could have a confidence interval that the lower bound is like 10 and the upper bound is like 19 or something like that. Okay, so that would suggest that your distribution is skewed because your fixed effect is basically the mode of that distribution. Okay, generally they're going to be roughly symmetric though. The only time that you will see that not being the case, at least in my experience for the most part, is on random effects. So specifically with like correlation parameters. Okay, so here's an example of the output from confint on mslopes, and this will take a little while, right? For this model is pretty simple. It'll still take maybe 30 seconds or so, maybe even a little bit longer. But for really complicated models, this could take a long time. This is for some of the models that I have run for papers where the model itself is quite complicated. I have set it up to run and then got it going, and then gone to sleep for the night and woken up to them being done, hopefully. Sometimes it's not always done still. But the other thing that's a little bit tricky about this is you sort of have to, it doesn't tell you the random effects that it's referring to. So you sort of have to match them up. You can figure it out pretty easily. So if we go back here, so we've got, right, 0.75, 0.27, and 0.29. So 0.7, so this is going to be the intercept confidence interval. And then this one's going to be the slope confidence interval. And then this is the correlation between them. Okay. And so that, like I said, that is generally how I would report it, is just here's the random effects, here's the confidence intervals on them, and we'll go forward with that, right? And then these are the fixed effects. If you want confidence intervals that are less computationally intensive, you can use the Wald method. That'll get you confidence intervals for the fixed effects, but not for the random effects. Okay, and there are other issues with that too. So generally, I think I've seen people recommend like you can use Wald as like quick check, but if you're actually going to publish them, then you probably should use an alternative method. The sort of gold standard for these confidence intervals is to use bootstrapping. Okay, so then you would just say confident method equals boot, I think. You could look at the help documentation. And then that'll do, there's a couple of different options actually, whether you want to do parametric or semi-parametric or whatever. But basically it's going to just do bootstrap resampling on the model. And so that takes even longer than the profiled confidence intervals, but that's generally considered like the gold standard for these. I tend to just use profiled because in my experience anyway, most of the time, the profiled confidence intervals and the bootstrap confidence intervals are very, very similar. And that's why profiled confidence intervals are the default. But you know, if you're feeling nervous or you maybe do the bootstrap confident, if you do the bootstrapping, then just go with those results. The problem is just that it takes a long time and you might need to have a lot of bootstraps to get to a stable estimate. Okay. All right. Yeah, that's the other thing Lindsay said in the chat, is that if you use method equals boot, you might get occasionally where you have convergence warnings. And that's probably okay. It's because you're working with only a bootstrap resampled version, right? And so that version of the data set might have like super low variance for the slope for one of them, because it's essentially like fitting the model a bunch of different times, right? Like you're fitting the model like 500 times, and in a couple of those, you might end up with cases where you have almost no variance in your slope. So then you end up with a convergence warning for that specific fit. And generally, that's not going to be that big of a deal. If you have like tons of warnings, then you'd probably be more concerned. Other questions, thoughts? All right, so the Elmer test library is sort of the other option. So we'll say library Elmer test, mslopes 2, and then you can just fit the model there. And then when you call summary on it, you'll get the output that I've been showing this whole time, where you have p-values and degrees of freedom. But you can see these degrees of freedom are like weird, right? 400.87. It's because they're estimated denominator degrees of freedom, and it for the F test, and it's makes assumptions that are reasonably met in specific like experimental designs, but not always clearly met in other situations, including growth models. All right, so last thing here before we move to the lab. Let's say we now have fit these couple of models, right? We fit the unconditional model, which was just the random intercepts model, and we fit the random slopes model too. So how do we know which model is preferred? How do we know which model we want to go forward with? Okay. Before I get to this, I will say that you should probably be careful with your language around this. You are not finding the correct model, right? Hopefully that's clear. But even the idea of model selection, I think, can be a little bit problematic, right? What you are doing is comparing the evidence across models to say which one has the best evidence for fitting the data the best, right? So I would encourage you to think about it more in terms of model comparison versus model selection. Okay. All right. So how do we know which model is preferred though? Like if we're going to go so if I were writing this up for publication and these were the only models I was comparing, I would probably actually report the results from both models, say the evidence suggests model A or model B, but present the results from both models, right? So that's part of what I mean for model comparison versus selection. Because if we're in the world of model selection, we would probably just select a model and then present that model. Whereas I think it's better to show all the evidence as much as you can. And you always have space issues and things like that with articles, so it's a little bit hard. But so when we're comparing models, we don't want to overfit to the data, but we also don't want to underfit to the data. Okay, so I want to just pause there for a second and remind us all, what do these terms mean? So think about that for a second, and then if you feel comfortable, please just go ahead and unmute and give me your definition for what these terms mean: underfit and overfit.
I tend to think of it as like being, either too general or too specific, and then they're not really generalizable or best fit to your sample. Like you could fit to every single point, but that's not necessarily a good representation of your data. But if you underfit and you're not specific enough, that's not necessarily going to be, again, a good representation of what your data are telling you, what shape they might be telling you.
Good. So which of those that you were referring to would be overfitting versus underfitting?
Overfitting would be like connecting each one having, you know, a very sort of complex looking fit, whereas underfitting would be having, you know, maybe a single line through data that's actually cubic or parametric or something.
Good. Perfect. So that's exactly right. And one of the ways that I tend to think about this is your data has information in it, right? That's why you're modeling it, is to try to get the information out of it. And but your data also has error in it, right? And that error might be measurement error. It also might just be sample specific things that are specific to your sample and do not generalize to other samples. And so you don't want to fit to those features of your data. You don't want to fit to the error of your data. You want to fit to the things that are generalizable beyond your sample and not your specific sample, okay? And so one other way of thinking about this that is more like machine learning speak, but is your model learns from the data, right? That's how it estimates the parameters. So you want it to learn from the data what the patterns are, but you don't want it to learn so much that it's reproducing the exact same data that you have, because then that's overfitting and you're not going to generalize well to new samples, right? So that I had a student actually that was talking about this in terms of like a tailor, somebody who makes clothes, right? And if you went to a tailor and they made clothes that fit you exactly, that would be great for you, but those clothes probably wouldn't fit other people as well, right? Whereas like the clothes that I buy, right, like just whatever, they have to fit a lot of people. And so they're designing those clothes to fit a lot of people and not overfit. But we don't want to underfit either, where we're wearing like really baggy clothes or something like that, right? Okay. So there's lots of ways to approach model comparison stuff. One of the main ways that we typically do this is through chi-square significant tests of the change in the model deviance. Okay, so this is probably what you did last term. We can also use information criteria, so AIC and BIC, and then there's cross-validation procedures and things like Bayes factors, which I'll show in a second too, which I'm not a huge fan of, but they are an option out there. Okay, so using the built-in approach, we would just call ANOVA on our two models, and we would get this kind of output. So just looking at this output for a second, how would you interpret this? Which model has the better evidence for fitting the data?
The random slopes.
Okay, why?
Because it's significant, and the way that I think about this, the significance test is the amount of variance explained worth the extra degrees of freedom, and if it's significant, then you go with the one with more degrees of freedom.
Yes, good. So looking right here, we see a p-value that is significant, right? It's less than 2.2 to the e minus 16. So that's 0.00000. And the chi-square value is also very large. So we've got basically two parameters extra that we've estimated, but the change in the model deviance is a lot. And so if and it's 105, right? And so if we, or maybe that's the log likelihood, whatever. And so if we just look up that value on a chi-square test, we'll see it's really unlikely that that change is due to chance, right? That's what the p-value is telling us. And so we would conclude then from that chi-square test that the M-slopes model is displaying the better fit to the data than the M-intercepts model. Okay, we also have in this same table 2 other indicators, AIC and BIC. Okay, these are both different information criteria, Akaike's information criteria and Bayesian information criteria. And they are scale dependent. So that means, right, the actual values that you see are completely meaningless on their own, completely meaningless. They are only meaningful in comparison to other values, okay? So from the same fitting process, right? So I have this model and this model, they're both fit to the same data. I can compare those 2 values, okay? And lower values indicate better fit to the data. And both of these, they work a little bit differently, but they both include penalties for the number of estimated parameters. So as the number of parameters go up, your information criteria is going to go up also. But that's relative to the log likelihood. And so if the basically explained variance is going up, your like residual variance is going down. And so your AIC and BIC are going to go down. And so if you estimate more parameters, but you're actually not accounting for any more of the variance, then your AIC or BIC values will go up. But the extent to which those still go down, you're having evidence that that model's fitting better. These are both going down by a lot, right? So over 100 for that one and that one for both of them, okay? And so like there's sort of rule of thumb in terms of like the delta values, the difference between those in terms of when it's like meaningful. And there's an article by Burnham and Anderson that I can find for you, but they recommend like any value greater than like 10 is displaying strong support for the one model, the model with the lower value relative to the other. Okay, and so this is way more than that. So we have pretty good evidence here through those 3 different criteria. They're all suggesting the same thing, the M-slopes fits better. Okay, there's also this performance package. There's these R-square values, which I would probably never report. I just haven't ever really looked into it, but it seems weird to me. So I just kind of innately don't trust it. But I haven't, like that's with me fully saying I haven't completely looked into it. This conditional one is saying the R-square when accounting for the fixed effects and the random effects, and this R-square marginal is just the fixed effects. Okay, so that's basically what it is. And it's not like that complicated, it just seems weird to me. You have like these conditional ICCs, which I wouldn't worry about too much either. But then you have the AIC and the BIC. You also have RMSE, which is kind of nice, and then just the sigma value. So you can compare those that way. And then you can do the likelihood ratio test like this. And then the last one from the performance package is using Bayes factors, where you would say test performance. Okay, and it will either do this log likelihood test or it will do Bayes factors. If you have a Bayes factor value of greater than like 30, generally, again, rule of thumb sort of thing, then that's really good evidence that the model that it's comparing to fits better. Okay, so M-slopes fits better according to the Bayes factor. So quick note on Bayes factors, right? You may or may not be familiar with them. You should know that they are fairly controversial, and people who are like pure Bayesian people hate them. They hate them because a huge reason why people like Bayesian methods is because it sort of gets us away from p-values, and we're sort of combining information from our prior expectations to the evidence from the data, and then we're combining it to get this posterior distribution that we use for inference. Okay, Bayes factors sort of like skip past all that and say, okay, is there a difference though? because that's all I care about, right? And so some people refer to them as like the Bayesian p-value. And like I said, a lot of people prefer Bayesian methods in part because they don't have p-values. Okay, so if you're going to use them, just be aware that you might get some pushback from some people. This is just a little bit more information about them. This would be my recommendation. If you're going to use them, which I am not saying don't by any means, but if you are, I would use them in combination with other things. So you could say, AIC says this, BIC says this, the tested log likelihood said this, and the Bayes factor was this, right? Oops. So you can see more information here. This is from the actual package talking about them. All right, final comparisons, and then we'll go to the lab. This is now just for 3 students, but we're looking at the prediction with the intercept only random versus the slope random, okay? So you can look at the trends here, and you can see that the difference for these 3 students is small, but you can see in each case it does look like the sort of orangish line there is probably the better fit to the data. Okay, we can go 3 more students, and for some of these, like this one and this one, the difference is like none, essentially, right? And so if all of our data points or all of our participants look like this, then we would probably have evidence that the random intercept model is preferred. But because we're having many that are looking like this, then, and here's 2 more though, right? So this is, and we could continue to do this more and more, but this is giving us evidence that the random slope model probably is preferred, but it's maybe not as overwhelmingly as some of that other evidence would have suggested, right? Because the differences are there and they're important, but for many students, the difference is none, essentially. Okay, so the slope variation is pretty low. So that's sort of the final conclusion. Given the evidence that we've looked at here throughout these models, I would conclude that both models are a considerable improvement over linear regression. I probably wouldn't include that in my write-up, but that is something I would conclude. And that the random intercepts and slopes model, so the one where we're allowing each individual to have a different slope, fit the data better than just random intercepts. There's more variability in initial starting point than there is in rate of change, but that's typical, right? So where students start, there's usually a lot of variation there. The rate at which they grow, there's also variation, but it's usually less than the initial starting point variation. Modest correlation between the intercept and slope, suggesting those who start higher also have steeper rates of change, but it was small, okay? So that's it for today. We're going to move to homework 1 now, and then next time we'll talk about model predictions and visualizations. So any questions before we move off of that? Okay, so let's go to, actually I can just go back here, I think. Yeah,
I actually have a question. I was trying to remember what we need to submit for like the week 1 and week 2.
Yeah, so when you are following along in class, you should have an R script or an R markdown file or something, and basically just submit that. Whatever it is that you're using when you're following along, just submit that. That just gives me evidence that you did follow along, and then I'll give you the 1 point. Okay. All right. So here, go to the website if you're not there already. And then there's 2 ways you can get to the homework. You can go to assignments, and then it's linked there. Or you can go to tags, homework, and it's linked there. Okay? So once you get there, this is what we're going to be doing. Okay? So there's sort of 3 primary purposes for this homework. And you'll see the last one is creating, well, it says a few. It's actually only 1. Creating 1 plot that looks like that, basically. Okay? That is from your model results. That part we haven't gotten to yet, right? That's the topic for next week, but this isn't due for 2 weeks. So that's why there's 1 question related to content we haven't gotten to yet, okay? The first 2 parts we should be familiar with now, we're going to start practice restructuring data in a format that would be appropriate for LME4, basically. And then we're going to fit some basic models through that, okay, using R. So getting started, create a new RStudio project, create a folder for the data, and place longitudinal sim.csv in that folder. Okay, that should be up on Canvas, or it's in the repo if you've cloned it. And then when you read in, so that's just getting started stuff, right? Then you're going to have our markdown file. Please just make it clear which question you're addressing at each point, okay? Part 1 is going to be about data restructuring, okay? So when you read in the data file, it's going to look like this. You've got G3, fall, winter, spring, G4, fall, winter, spring, G5, fall, winter, spring. And so each row in the data set represents a unique student who is nested in a school, which is nested in a district, okay? And I'm asking you to restructure this data set so you can use it for LME4, where you're coding time by wave. So there are 9 waves here total, right? 3 waves for each grade. And so it should go 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. And then you should, by the end, make sure that you have a grade column too. So you don't want to lose the grade. You want to know what that is, but you should have the grade and the wave. Okay. Then we're going to fit a model, or a couple of models. So we're going to do an unconditional growth model with random intercepts and parallel slopes, a conditional growth model with random intercepts, parallel slopes, and a grade level fixed effect. Okay, so we're just going to include grade as one of the predictors. And then an unconditional growth model with random intercepts and slopes. And then a conditional growth model with random intercepts and random slopes and grade level fixed effects. Okay, so I realize we didn't get to including other predictors, but I'm not asking grade level to vary randomly. I'm only asking for wave to vary randomly, right? So that grade level fixed effect would just be like plus time point plus grade plus then your random effects. Okay. For models 3 and 4, I ran into some convergence issues, so I gave you a bit of code here if you want to avoid that. It actually makes no difference, really. I fit it with a whole bunch of different optimizers, and the results for both the fixed effects and the random effects were essentially identical out to like 3 decimal places. So, but some of the optimizers complain a little more. Okay. Part B is just going to be compare the performance across those 4 models. And
can I have a quick question there?
Yep.
So in the paragraph above that, I thought you said fall, winter, spring will be 1, 0, 2, not all the way from 0 to 8, right? So
yeah,
we will have.
So I just gave an example, code time by wave, e.g. fall, winter, spring, from grade 3. Anyway, 0, 1, 2. So basically what I'm trying to say is don't code it by like, don't try to code it any more fancy than that. Just 0, 1, 2, 3, 4, 5.
Yeah, so that means for each grade you have 3 waves, and then the next grade you just continue until 8.
Yeah.
Okay. Yeah.
You could actually, yes, you could do it the other way too, but that ends up a little less clear. So as you can see down here, I coded waves 0 to 8. So that's how I would recommend.
Thank you.
As well. And I can edit this to make that a little more clear. Okay, so then part B, you're going to compare the performance across those 4 models and do a brief write-up to tell me which model you think has the best evidence for fitting the data. And then the last part, provide a brief write-up interpreting the model that you think has the best evidence from part B. Okay. And I'm looking for like plain English description. So it can be APA or not. I don't really actually care about that at this point. I'm looking for you to interpret the parameters, right? So the fixed effects and the random effects, interpret those and just tell me what they mean. Not like this is what, confidence interval of blah, blah, blah. Although I might have said something about confidence intervals. No, I don't think I did. Okay, so this is really, I'm just looking for a plain English description of what you think this model actually means. Okay, so that's all the stuff that we've sort of covered from today. And then the next part actually probably won't be that difficult, I don't think. But you'll produce a plot just like this, but for student 111, 112, and 113 instead of 114, 115, and 116. Okay, so, and again, we will get to how to produce those next week, but you should be able to do all the way up to here without, well, based on what we've covered already today. Other questions?